Okay. All right. First of all, thank you again to Samuel and Cheng and Yang Wang and the University of Miami for hosting us. We always enjoy going to these events, and rekindling our collaborative efforts over the years. I've known Samuel for 12 years and keep going. So, as I mentioned yesterday during the flash talk, I briefly talked about two main products, and everyone here got a chance to see them in person yesterday. They're the Nanosite Pro and the Zeta Sizer. And so between those two techniques, you get a number of metrics, namely the nanoparticle tracking analysis, and fluorescence and concentration with nanosite. And then you get dynamic light scattering and electrophoretic light scattering, or sometimes people know it as zeta potential with the Zeta Sizer. So let us start off with the Nanosite Pro, which utilizes nanoparticle tracking analysis. So from the get-go, why would you be interested in this technology? You can get size, you can get concentration, because it's a number-shaped distribution, which I'll talk about. You can get a good sense of heterogeneity in your samples if you've got some really highly dispersed samples. And if you happen to look at fluorescently labeled particles, you can distinguish the percent labeling of your population compared to the total population. So there's a number of applications across the board that use this technology. Nanosite's been around for over 20 years. And so a lot of the different, fields of study involve extracellular vesicles or exosomes, drug delivery, vaccines, this big bucket term of called nanomaterials, so anything that's synthetic.
Sorry, no, but is it okay if we take photos of this lens?
Yeah, sure. Yeah, I'm not presenting anything that's not public, so. If I was, I'd close the room and tell you guys. I'll keep it on. All right, so yeah, feel free. Protein aggregation, and then there's a whole separate field called nanobubbles, which we can talk more about. So, how does it work? We have a laser module that inserts into the main system, right? You already saw a picture of it on the first slide. And that laser module has a prism that sits at an angle, and it has a diode laser that sits at an angle and propagates through that prism. That prism will then scatter the beam into a suspension of particles that's sandwiched by a top plate. The top plate contains the sample over this chrome-coated glass prism. And what you're doing is you're seeing the light scattered off the particles move around in Brownian motion with a high sensitivity camera that's off the diagram here, a 20x objective lens, and then you have your laser model. So what you're going to do is you're going to capture videos of the light scattered off these particles moving around in Brownian motion. And then you're going to process those videos where we're going to actually note the red Brownian motion tracks on a particle by particle basis. We're looking at the mean square displacement, of that particle on a frame by frame basis. And then you get your high resolution data in terms of concentration versus size. So here's an example of what the field of view would look like when you're operating the instrument. You have the light scattered off the particles, not a direct image. So just to clarify, it's not like SEM or TEM, like a live view of that, right? Because sometimes people will say, oh, that particle looks bigger than the other one. Well, if you have a big dot and a small dot, and they're moving at the same diffusion speed, they're the same size. It just so happens that that large dot might reflect a particle that's denser or has a higher refractive index and thus scattering more photons than its neighbor. But if its diffusion speed is the same, that means it's the same size. So, as I mentioned, we look at the mean square displacement of those particles on a frame by frame basis. So that means we can actually use a version of the Stokes-Einstein equation that will calculate the hydrodynamic diameter, where you see temperature and viscosity being dictating variables that affect that relationship between the mean square displacement and the hydrodynamic diameter. The software automatically notes the ambient temperature. You can control the temperature if you need to for specific experiments. You can go from a few degrees below ambient up to 70 degrees Celsius. You can do an isothermal experiment, thermal ramp, and so forth. but it's not a requirement to do, just some standard measurement. You can leave the software to just note the ambient temperature, throughout the measurements. So if you're recording a video that's say five videos and the 0.1 or 0.2 degree difference in between those videos, the software will note that and adjust its calculation. Viscosity, you can handle viscosities up to about 5 centipoids, which in the big scheme of things is not very viscous at all, because we still need to see the particles moving in a very fluid fashion to note their mean square displacement. Note the time, because I'm trying to get you stood up yesterday to say, hey, stop talking. Okay. How we calculate concentration is that we look at the field of view and we note the number of particles that per frame. And the software knows the third dimension. It'll calculate an observational volume, and then from there it'll calculate the concentration in terms of particles per mil per frame. So you can record 1,500 frames in the course of like 20-30 seconds, and you get a pretty absolute number average for concentration in terms of particles per mil. So with any technique, there are going to be limitations. We think of those limitations in terms of size and concentration. On the low end, it's about 10 to 40 nanometers. The reason there's a range at the low end is because that primarily has to do with material type or in the refractive index. So if you're working with, let's say, metals and metal oxides, those will have a higher refractive index, and you can push that limit down to 10 nanometers. We more than comply with ISO standards, ACM standards, and we show 10 nanometer silver particles or 10 nanometer gold particles to verify the lower limit. If you're working with synthetic based particles, biological based particles, your lower limit might be more like 40 or so nanometers. On the other end, it has to do with anything that's going to retard the Brownian motion. So whether it's the inherent size of the particle, or if you've got a smaller particles, but it's the viscosity of your dilutes. So the upper limit is about 1,000 nanometers. The other metric we think of is concentration. On the low end, it's 10 to the 6, 10 to the 7. It just becomes a matter of statistics, having enough Brownian motion tracks to get good, reliable, and reproducible data. And then on the other end, it's about 10 to the 9 particles per mil. Because it gets to a point where if you're looking at your field of view, you might see a thick ocean of particles. Well, the software is going to have a hard time distinguishing one track from another, right? It needs to see discrete random walks. And so with the upper limit, you lose that reproducibility. And you get a lot of cross-tracking. So the latest and greatest is the Nanosite Pro. We introduced that in the summer of 23. And we've improved its automation. We have machine learning. There's a lot of detailed quality guidance. You can customize PDF reports, and just the total operational time is about 2 or 3 times faster than a lot of the previous generations of Nanosite. So when you get your data, you get your mean, your mode, your standard deviation. You get D10, D50, D90 values, and then your capture conditions and so forth. And then we also introduced a different way of looking at quantum dispersity, and that's span. Span mathematically is D90 minus D10 divided by D50. So the frame of reference is that if you're looking at monodispersed samples, let's say the size standards that come with your system, those would have values between 0 and 0.5. If you're looking at well-defined, synthetic or biological samples, then those might be 0.5 to 1. And then anything else that you see here with multiple populations would be any value above 1. It's a limitless metric of quantum dispersity. Because it's a number-based distribution, it means that we're taking data points, per size, and we're putting them into different bins. And when we do that, it enables people to actually calculate, the percentage or the concentration of different ranges. So if you're doing some sort of quality control analysis, or you want to fine-tune your process, and you're trying to say, I need particles to be between 46 and 212 nanometers, you can actually set that numerically in a plot range option right here. And you can set up 3 different gates if you wish. And then you can also it'll report the concentration of those ranges, or if you toggle the percentage option, it'll convert that to a percentage of the total population. So, in addition, when you're making a measurement, I didn't say this before, but there's pre-capture analytics, so you can look at the live view, you can get a sense of what, a preview of your distribution while it's in live view, and it'll give you some pre-capture analytics. It'll tell you, look, your concentration is too high or too low, or you're using the syringe pump too, infusing it too fast. It'll give you all of these things before you even record videos. So there's pre-capture analytics, but then there's also post-capture quality guidance. And so you can actually get a sense and better confidence in your data. So here's an example where it'll give you some trend analysis. So if your sample is aggregating or dissolving pretty quickly, it'll note that in terms of the size, at incremental frame numbers within a video and across multiple videos, and it'll also note the particles per frame. So if your sample is quickly aggregating, you might find that across multiple videos, your size is increasing, and then your particles per frame is decreasing, right? Because as particles come together, you have fewer number of particles. And in addition to that, you have also data quality guidance. It'll scrutinize all these different parameters. And if there's an issue with one of them, it might show an empty green icon. A full green means no issues. Empty green means that there might be a few considerations. And it'll tell you issues identified. How can I use this data? How can I improve this data? And it gives you paragraph-long responses. So you can be confident in the analysis you're performing. In addition to the size and the concentration capabilities, we can look at fluorescence. So if your research dictates that you're tagging particles with certain fluorophores, you would come and talk to us about what fluorophores you're using, and then you pick the corresponding laser wavelength. You can select up to 4 different wavelengths at one time and get a fully loaded system, or sometimes people look at a couple different wavelengths. But the premise is that you're going to get a laser module regardless. But then if you are looking at fluorescence, you would get the corresponding long pass filter installed inside the system. And what we're doing here is, we're first looking at what we call a scatter mode, right? That's the total population, that's the absence of any fluorescence filters. But then when you insert the fluorescence filter, you're now looking at just the labeled population. And what the software is going to do, it's going to now have this protocol set up for fluorescence where it automatically looks at the scatter mode, the total population, and then immediately inserts the filter and looks at the fluorescence mode. And then it will overlay the two, and it'll calculate percent labeling efficiency of your population. So you can see here in this particular example that we've got pretty good labeling. We've got about 86% labeling efficiency for this particular sample. So some examples. There's a lot of different examples, and I know everyone's research is different, but this is just a taste of the data that you get. So exosomes is a very big field for nanosite users. And so exosomes are often used to identify diseases. And so here's an example where, a non-pregnant patient has very minimal concentrations of exosomes. A healthy pregnant patient has, a bit more in terms of concentration of exosomes. But then someone who might unfortunately have preeclampsia during pregnancy will have a statistically significant number of exosomes. So that's just one example. You can also look at aggregation. So here's an example where we're looking at IgG aggregation. And you can note the kinetics, where you see an increase in concentration and size over the course of 300 minutes, where you can set up your protocol and take, time points of various time points and look at that growth. So IgG, it needs to aggregate to about 30 or 40 nanometers before we actually can start tracking its change, right? In its monomer form, it's a little too small for direct analysis. But once it aggregates to about 30, 40, we can watch that growth. So you can get monodispersed populations where we see the mean, the mode, in close agreement with one another. The standard deviation in this case is only 5.9 nanometers, and then you have D values and a high concentration. So this is, you know, a well-defined monodispersed, you know, sample of liposomes. Polymer nanoparticles might show a little bit of aggregation. You can see that displayed in the size and concentration graph. So you can see the standard deviation in this case is about 55 nanometers compared to the 5 nanometers we just saw. Lentivirus, you can look at viruses, you can look at aggregates, enveloped virus and unenveloped virus. You can also do some quality control. So this was a group that they were making polymer-based nanoparticles, and they were probe suffocating them. Their target range for their process was to get particles between 45 and 65 nanometers. So their pass is what they're calling, you know, every pulsing for their sonication. So first pass, very minimal percentages were in their target range, only 0.17%. But then as they went through a third pass, they were starting to get more into their target range, about just shy of 30%. And then by 10 passes, they were getting an overwhelming majority of their sizes within that target range, 78.1%. So you get the idea that you have a number-based distribution, you can gate, and you can get a better understanding of your quality control. Liposomes, again, is a big field, and you can look at how you prepare liposomes, whether you subject them to freeze-thaw cycles, or if you're going to extrude them, you know, sequentially through different size membranes. You start with a larger size and then work your way down, you know, to smaller sized membranes to get your target size for liposomes when they're well prepared. And you can see the effects they have on not only the concentration, but the size as well. So the pore size, you find that if you do step down extrusion and you do a freeze-thaw cycle to reorient the lipid bilayers, you can actually get some pretty high yields of liposomes. So if you're interested in more in liposomes, I did a whole 3-part webinar series and a lot of content around them. So that's nanocytes kind of in a nutshell, giving you some examples of its capabilities and applications. Let's switch gears and now let's talk about dynamic light scattering. Dynamic light scattering, we have 6 different iterations of the zeta sizer. They all measure zeta potential to the same capability, but then where they differ is their size. So we think of categorizing these zeta sizers in a couple different ways. One is by laser power. We have the blue label systems, which utilize a 4 milliwatt laser, and then the red label systems that utilize a 10 milliwatt laser. So if you've got some weakly scattering biologic samples, sometimes people will refer to the red label systems, but otherwise, if you got hardy samples, you'll be more than the blue label systems will be more than sufficient. So that's one way, is by the probes, right? Blue label, red label. The other way is by the angle of detection, and I'll talk about that here in a moment. Well, we have the side scatter angle, which is denoted as the lab. We have what we call the non-invasive backscatter angle, which is used for more concentrated samples, and that will be the probe. And then we have the ultra, which the lab has a side scatter, probe has backscatter and forward scatter. You can imagine that in our whole marketing, plan, we have the ultra that has all 3. So we have the backscatter, side scatter, and forward scatter, and that can benefit from, that has some extra benefits as well. So when we talk about dynamic light scattering, it's a non-invasive technique that looks at particles in suspension. We're still looking at Brownian motion, so there's a lot of similarities between the zeta sizer and nanocyte in that respect. Then we still look at the diffusion movement of these particles undergoing Brownian motion. Oops. Video. So Brownian motion, again, is the idea that when we're talking about particles moving around, they're being bombarded by solid molecules. So smaller particles will move faster and larger particles will move slower. Okay. So when we talk about Brownian motion, with the zeta sizer, we're looking at the diffusion coefficient.
Someone needed microphone batteries? Not you?
No, he's on.
No. Yeah, I'm good. Well, I talk about it. Thinking more than that. So, When we report the diameter, we're reporting the hydrodynamic diameter, the spherical equivalent of your particle moving around in ground motion. Right, so if you're taking this mic, you know, this is rotational diffusion, translational diffusion. Translational diffusion will note the hydrodynamic diameter, which might reflect a longer dimension. Okay, I hope it won't instruct anybody. So that might consist of your core particles plus any ions, any grafting of polymers around it, the shape. You know, all of these come into play when we talk about the hydrodynamic diameter. And that goes for the nanosite discussion as well. That's just, you know, basic light scattering. So when we talk about the dynamic light scattering, if we suspend physics for a moment and we say particles are completely static in solution, then when they experience a laser beam, see an incident laser beam and scatter photons, the photons will present a static signal at a detector. But because particles are constantly moving around in random motion, the signal at the detector is going to fluctuate. So what we then see is the frequency of that fluctuation is dependent on the size of those particles. So if we're looking at smaller particles, so let the video catch up, you'll see a frequent intensity fluctuation. And then if we have larger particles, you'll see a less frequent fluctuation of the signal. Okay? Video has to catch up. They got a cool British accent if I was to turn on the video. So sorry, you just have to hear my voice. So smaller particles, rapid fluctuations, larger particles, slower fluctuations. So then what we do is we're looking at this signal, and we're going to take rapid snapshots in time and compare the signal change back to time zero. And that whole process is called autocorrelation. So we see here, we have time zero, the original signal, but then as time progresses, we're going to plot the correlation coefficient over time. And the time points are on the order of nanomicroseconds. So you can see a decrease or a decorrelation as time progresses. So it gets to a point where as time progresses, the signal will completely decorrelate. And so it'll come down to a baseline, right? So the correlation coefficient will ultimately go to zero in most cases. So then what we can use this to determine, you know, the character of particles. So if we look at larger particles, they move slower in grounding motion, they'll decorrelate slower. Smaller particles will move around in grounding motion quicker, so they'll decorrelate quicker. So that's ultimately what we're doing. We're looking at the correlation coefficient over time. We ultimately get our diffusion coefficient, and that's the Stokes-Einstein equation that we use for the dynamic light scattering, where we look at the hydrodynamic radius or diameter. So the corellogram, you know, we always try to make sure people veer away from black box mentality, right? You can stick some poorly characterized or poorly prepared samples and still get size frequency. But it's important to understand the corellogram, right? The corellogram is going to tell you different characteristics about your sample. So we start with the y-intercept. We talked about at time zero, the signal should be a one-to-one overlay. There's always going to be some level of aberration, so it might not always be at 1, but if your sample is, you know, has an intercept between 0.7 and 1, that indicates a good signal to noise ratio. So that's the first part. The second part, we've already kind of hinted at, right? The onset of decay tells you about the size of the particles. If you have a prolonged onset of decay, it means you've got larger particles. If you have a quick onset of decay, it means you have smaller particles. And then the nature of the decay. If you have a steep cliff, that means all your particles are pretty similar in size. You know, they moved around in grounding motion at a similar diffusion rate, and so they decorrelated at the same time. So that would indicate a more monodispersed population. If you have a shallow decay or a step decay, that indicates you have a more polydispersed population. And then the final part is the baseline. The baseline is going to tell you about the presence or absence of any large scatterers, contaminants, dust, what have you, inside your sample. So it's important to understand and, and reflect on the different parts of the parallelogram before you even consider the size distribution. And the software is smart enough that it's going to give you the very detailed quality guidance, similar in nature to what I just showed you with the nanosite. It's going to say, issues identified. How can I use this data? How can I improve this data? And in that quality guidance, in the hidden layers within the software, it's scrutinizing these different parts of the parallelogram, plus some other factors in the measurement. So, a little bit of summary is that you have small particles with a frequent intensity fluctuation. We look at a linear time axis, you can see the correlation coefficient quickly decreasing. We plot the parallelogram on a logarithmic time axis to give you a breadth of view, and so you can see a quick decay. Conversely, large particles have a less frequent intensity fluctuation, slower decorrelation, and then, on a logarithmic time axis, you see the pronounced and prolonged decay.
When you say that the baseline tells you the quality, is that you don't want any peaks on the baseline.
Yeah, so sometimes what happens is that if you've got, dust or contaminants, in the presence of your main population, it might present a noisy baseline or a raised baseline. And sometimes just along that point, if you've got large particles, very large particles, but are lower concentration, they might present as number fluctuations. Meaning that if you're looking at your scattering volume within the cuvettes, you might have large particles popping in and out of the scattering volume, offsetting your count rate of photons, and then how that will present is a nonsensical y-intercept. As we just said, the theoretical limit is 1, and it'll present a y-intercept that's above 1, and that's often coupled with a raised or a noisy baseline at the end of your parallelogram. Okay? Yeah, thanks for that question. So we apply an algorithm to get from our parallelogram to our Gaussian-based distribution. The key here is it's a Gaussian-based distribution, right? So you're not going to gate, or anything like that, with a zeta size. And we can look at the distribution in a couple different ways. We can look at something called the cumulative fit. It'll give you the overall average size and the biodiversity index, which is often used for batch-to-batch comparisons. If you've got multiple populations within, 2 different batches, you can use those as quick comparison metrics. And if you do have multiple populations, the software is going to encourage you to consider the distribution analysis, where it will give you the peak by peak sizes and the standard deviation within those peaks. So, switching gears, noting the time here, we have electrophoretic light scattering. So, electrophoretic light scattering is the movement of particles in relation to a liquid under an applied electric field. And essentially what it is, it's a metric of colloidal stability. We can look at, using DLBO theory, we can look at electrostatically stable particles, and the more stable your particles are, the higher the absolute value your zeta potential will be. So, regardless of charge. But the higher the value, the more colloidally stable your sample. So a lot of people will consider this for shelf life, product shelf life, long-term stability, and so forth. And then I always find it interesting to mention the water treatment facility industry. Water treatment industry don't want things that are safe, right? That's essentially what they're doing. We take the raw water, which might have a high zeta potential value, and they're putting coagulants to get as close to 0 millivolts as possible, because that's how they crash things out of the water in their purification process. So, good data is in the eye of the beholder, depending on the application. So, when we talk about zeta potential, people sometimes have this misconception saying that, oh, it's the charge on the surface of my particle. That's half the equation. That's not even really the proper half. What it is, it's the electrostatic interaction between charges at what is called the slipping plane. Or if you think of this like an atom and valence electrons, I like to use the word valence. It's the valence charges around your particle as they interact with your dispersant. Meaning that if you've got your core particle, let's say, with whatever charges might be around it, and you're looking at it in buffer, and you take that same core particle and you don't change anything else, and you look at it in water, those 2 different conditions will produce different zeta potential values. So we need to be mindful of what is in your environment. So it could be the pH, ionic strength, anions, cations, electrolytes, all of these will come into play and affect your reported zeta potential value. So when we talk about actually calculating the zeta potential, we have to go back a couple steps. One is we're going to look at the electrophoretic mobility of your particles, which again is the movement of particles in relation to a liquid under an applied electric field. So in that statement, we need to consider the particle velocity and the electric field strength. So the electric field strength is determined by taking your cuvette. The software knows what the distance is between the electrodes, so you don't need to come up to the zeta side with a ruler. Don't worry. That's automatically determined. And then the applied voltage. So the applied voltage, most of the time, is automatically set for you. People in some cases, if they're looking at organic solvents, can do a voltage titration, for some reasons. But that's how you calculate the electric field strength. It's the applied voltage divided by the electric field, the distance between the electrodes. So that's the denominator. The numerator is determined by something called the laser Doppler effect. And what that is that we have a reference beam generated in the hardware. So you'll hear a buzzing sound when you make a zeta potential measurement. That's the reference beam of 1,000 hertz. And then we look at the frequency that's changed when that reference beam encounters moving particles. So from that process, we can calculate the frequency shift and then use the laser Doppler effect equation to determine our particle velocity. Because zeta sensors are all made with a 633 nanometer wavelength hitting the ion laser, and they're all measured at a 13-degree angle. So we know those two factors, and we now have determined frequency shift, so we can then calculate our particle velocity, which again goes back to electrophoretic mobility. And so that's how we calculate that. If you're like, Ruddy, you still haven't measured zeta potential. Yes.
Yeah, so you mentioned that when you want to measure the zeta potential, you should think about the displacement.
Yes.
So in case I want to change the surface CVD or is it your material, I should prepare a displacement which is opposite when the material is in the past.
You need to prepare a dispersion that will be in your target application. That will be, if you're looking for stability, that will stabilize your sample. Right? And when you are talking about the word preparation, let's say simply put together, polymer nanoparticles in a buffer. Right? If you need to dilute down your sample, you need to dilute it down in buffer. Right? So if you take your particles in the buffer and dilute it down in water, then guess what? You're diluting out your salts. And that's going to affect the electrostatic environment around your particles. So you need to be mindful of how you're doing it, because it's always the interaction between the particle and the dispersion. You have to consider both parts of that equation.
So, a follow-up question.
Yeah.
Because we are talking about profile. So, is there any optimal period for that buffer to get, what desired results, or to kind of confirm?
It depends on your own research. Okay. So I'll show an example where you can look at pH titration.
Yep.
You can titrate and figure out the optimal stability, right? And you can look at, isoelectric points, or extreme pHs might show really stable particles, in the acidic pH and the basic pH. But as you get closer and closer to the isoelectric point, that's the point of 0 millivol zeta potential. Your sample's not going to be stable in that region. Okay, so I'll show that example here in a moment. But yeah, thank you. So going back to this then, and again, feel free to keep asking me questions. The electrophoretic mobility we've calculated, but now we need to use that to calculate our zeta potential, because that's ultimately what we're trying to get. And we're going to use something called the Henry equation. So electrophoretic mobility is related to the zeta potential through this Henry equation, where the other factors are the dielectric constant, the viscosity, and we're using the Henry equation. There's something called the Henry's function, F kappa alpha. And ultimately what the Henry's function dictates it's a way of us looking at the polarity of your media, right? And the polarity of media affects something called the bilayer, the electrical double layer around your particles. So if you have polar media, water and so forth, you're gonna have a more compressed electrical double layer. You're gonna have a smaller, a thinner electrical double layer. And you're gonna use something called a Smolensky approximation. And then if you're gonna use more organic solvents or non-polar media, that electrical double layer is gonna expand out a bit more. And so you're gonna use something called a Huffle. And for those who are fastidious, you can actually look up the F kappa alpha value, the Henry's function value for your particular dispersion, and note that. So it's not a binary option. You don't just say small choppy or Huffle. You can have the option to actually put some value in between. Okay. So when we have our cuvette, we have our electrodes, we can apply the voltage in different ways. We can, because particles will respond to that voltage orders of magnitude more than, the liquid. And so we can apply something called fast field reversal, which gives a response, a chance for particles to respond, in their particle velocity to the applied voltage. And that will give you the overall Z potential value. You can also go back in, depending on the conductivity of your sample, you go back in and apply a slow field reversal, which will give a chance for the liquid to respond to the movement of the voltage applied. So essentially what we're talking about here, because I'm trying to wrap, say this in just a few minutes, is that fast field reversal will give you your overall Z potential value. Slow field reversal will give you the distribution of your Z potential. So let's look at some examples. For DLS, because you can look at Z average and PDI, you get a quick sense of how pure or how well defined your sample is. So, and the other thing is that the analytical range for the zeta size goes down to 0.6 nanometers, and you can go up to about 10 or 15 microns or so for size. So a lot of people will look at really small things, and you can get a good sense of purity and dispersity. So here's an example where we're looking at adeno-associated virus, AAVs, at 30.8 nanometers. 30.8 nanometers is a little bit too small for nanosecond. So you're kind of pushing the limits, with nanosecond. So a lot of people will use the zeta sizer to look at their AAVs. Lipid nanoparticles is another thing. You can get the Z average, quantum dispersity index, and you can see that they're relatively model dispersed. You can look at your purification. So if we're looking at these antibody drug conjugates, let's say, before purification, you can see that the Z average is 92.76 because we're reflecting larger particles. The PDI is 0.6, which is, on a scale from 0 to 1. Obviously, the closer to 1 you are, the more wide dispersed your sample is. But then after purification, we have a PDI of 0.06, and it's much smaller. So you get a sense of how well you've isolated your particles and purified them. You can look at thermal ramps, right? So you can get aggregation temperatures and also melting temperatures. When you're looking at, this sample of IgG in a buffer. And then there's some other structural information that you can get with the zeta sizer. So there's this concept called B22 measurement, right? So the B22 measurement basically looks at how, the structure of your sample, and you can use something a different version of the measurement in the zeta sizer called static light scatter, where we take the raw intensity value and then you're going to serially dilute your sample and plot concentration. And what we're doing is we're creating what is called a divide plot, where the intercept will tell you the molecular weight of your sample, and the slope will give you this B22 measurement. And so you can look at not only the B22 measurement, but you can also understand KD. And KD will tell you about the repulsive interactions or attractive interactions between with your sample. So if you have a positive KD, then that means your sample has a little bit more stability than a negative KD. So you can use the combination of B22 and KD to look at different formulations. You can see here with formulation 1, we have low stability and hydrodynamic based on hydrodynamic contributions. A positive KD in formulation 2 indicates more stable formulation and a low aggregation propensity and low viscosity. So there's a lot of information you can get about formulations and details, with the KD and B2 Yeah,
So, what actually is it, if I got a negative zeta potential, so based on your experience, what that negative zeta potential indicates in general?
so depends on, the negative means just the electrostatic environment presents a negative charge around your particles, right? But then the other part of that is, what is the value of that zeta potential? Is it -5 or is it -45? Right? If it's -45, you've got something that's really colloidally stable, right? It wants to stay in solution for a long period of time. If it's -5, then you might be looking at things that are aggregated very quickly.
Okay.
Right? Again, it's the two-part combination, right? It's the value and the charge. So here's exactly what we're talking about. Your question led right into the zeta potential examples. So if we're looking at extreme pHs, they'll have large values, positive and negative, right? Something that's colloidally stable. But as you get closer and closer to the 0 millivolt line, the pH at which we cross 0 millivolts is the isoelectric point. So up until this point, when I'm talking about the zeta potential and showing you examples, I've been talking about electrostatic stabilization, right? But there is a separate field where we'll look at steric stabilization. Steric stabilization presents the zeta potential a bit differently, in that you can have a particle, let's say, these liposomes, right? Liposomes have a lot of polar head groups around them. That's just the nature of their construct. And people will calculate that. I did this during my postdoc because it allows for better trafficking in physiological conditions. So that presents steric stabilization. However, what the PEG groups are doing is that they ultimately are physically shielding the polar head groups around that particle. So as you add more and more PEG chains, you're going to physically shield those charges. And so when you look at the zeta potential, you're going to see it decrease as you add more and more PEG groups. So that's where we couple both the zeta potential and size. I don't have it here, but there's an example where we look at a particle with dextran and a particle without dextran, right? And a particle without dextran, presents at a higher zeta potential value because it was, de-shielded. But when we look at other experimental conditions, it had a tendency to aggregate really quickly because it did not have that steric stabilization. And we noted that aggregation by size. So size and zeta potential marry really well when you are talking about steric stabilization. So you can look at, ionic strength. So you can see, alumina with potassium nitrate at different concentrations. You have ionic, low ionic strength, a high charge, medium ionic strength, medium charge, and then high ionic strength, low charge. And then there's a whole field of lipid nanoparticles where we look at ionizable lipids and various other types of lipids, the helper lipids and pegylated lipids. They'll have these different charge components to them. We can go through a full study and see the size, the zeta potential, the PDI, where people look at this, the encapsulation efficiency, zeta potential, polydispersity, size, and so forth, and then go through all these different conditions in their formulation to understand, what is the optimal formulation. So this is probably a point where we would work with fast formulator and, do the experimental side, and AI would take over and be able to, determine the optimal conditions pretty efficiently. So there's a lot of other examples of lipid selection. So again, you can choose the different lipids, look at their particle size, their PDI, their zeta potential, and encapsulation efficiency, right? So that's the benefit of that. And zeta potential ultimately for a lot of people is a metric of shelf life, right? So we cater to the bottling industry in a very big way. We cater to the pharma industry in a very big way. And you can see that, the shelf life is, proportional to the zeta potential value. The higher the zeta potential value, we see the longer shelf life in terms of months, it's plotted here. So, and then as I mentioned yesterday, there's a lot of similarities between the nanosite and the zeta sizer. Again, they both measure size, they're both light scattering based. instruments. They both use the Stokes-Einstein equation with their, relative, variations of that. They both require temperature and viscosity as part of the equation. They are looking at hydrodynamic diameter. And then a lot of publications, both benchtop, both, relatively small. You saw them in the lab yesterday. And they use everything. So differences again is that we're talking about nanoparticle tracking analysis, dynamic light scattering. Number-based distribution, so this high resolution, a little bit less resolution. Number weighted, intensity weighted. Smaller size range for the nanosite, larger size range for the zeta size. Concentration, not really dependent, you can see different particles, based on concentration. If you have a high concentration of large particles, that might overwhelm some of the smaller particles. So there is some concentration dependence on the zeta size. You can work ultimately with more dilute samples, or you need to work with dilute samples. We measure nanoparticle tracking analysis. You can work with some more concentrated samples. Samples could look a little bit more opaque when we're going to use the zeta size one. Low sensitivity to aggregates because it's a number-based distribution. There's a higher sensitivity to aggregates because it's with zeta size because it's an intensity-based distribution. And then, as I mentioned, you have concentration, size, and fluorescence for the nanosite, and then you have size, zeta potential, and you can do concentration with one iteration of our zeta size for a limited range. And with that, I thank you for your attention, and we'll have to take any other questions.
And we have a few questions now, and we also have a Q&A session at the end of the thing, yeah. So maybe we just, any quick questions? There's one quick question, correct? There's one quick question, yeah.
Oh, sure, yeah.
Thank you very much. So for nanosite, you mentioned that in the analysis we use this based on displacement.
Yeah.
So I wonder which reference that's there. Is it on the camera that it takes the first shot the commands and reference with?
Yeah, so that's a really good question. When we talk about grounding motion, we look at field of view, 2D field of view. We're going to note the x and y coordinates of that particle. On the first frame it sees, the software sees, and then look at, we do vector analysis. You look at, how far it moved to the next frame, the next frame, the next frame. Now, there's a threshold. It needs to stay in view for a certain number of frames, or it's counted towards the report. It's called a valid track, right? If it comes into view and out of view too quickly, it says, look, you didn't stay around the party long enough. It's not part of the valid track. So you might get plenty of tracks and get a fifth on prediction and reliable analysis, but you might get 10,000 tracks. But just know that you might have actually analyzed 3 or 4 times that much in terms of all the tracks that we're observing. Yeah, thank you.
All right, thank you so much, Jerry. So our next talk is from Jack who's going to talk to us about about overview of surface area and density measurement technology used in pharmaceutical manufacturing, and you're going to talk more about surface density and other aspects of it. Thank you so much.
Thank you. Thank you again. Thank you for having me and inviting me to the session. We talked. It's been first time here. I'm really enjoying it. I'm with Micromerdic System Corporation, which is now part of Melvin Analytical, as I mentioned yesterday. And today's subject, I'm going to talk about surface area and density of solid particles and materials. I'm going to start off with a few topics. What I call a pharmaceutical toolbox, and just what kind of instruments and technologies are available to make measurements so that we can make decisions on our materials. We give an introduction to physiabsorption or physical absorption and BET theory. Also give an introduction to gas and dry powder phytometry and the tools that are used for that technology or those measurements, a couple of case studies. So when we're talking about surface area, we're looking at specific surface area and porosity. So when you have a material, when you zoom in on it, it's not a perfect sphere. It has some features, it has some surface roughness and different things. The way it affects pharmaceutical manufacturing is it affects disintegration, dissolution, bioavailability, which is when you're talking about inhaled materials, how it can get there, how it reacts to the environment, blend uniformity, film coatings and adhesion, And then also USB monograph requirements. So in general, when we look at particle, we think of it as a sphere. When we do particle size, we're talking about equivalent spherical diameter. But in reality, particles are very irregular in shape. So we have to look at something else. Specific surface area is a measure of surface area per unit of material. So it's meters squared per gram is the typical units that we're reporting. They will affect the activity and reactivity because if you're trying to have some kind of reaction, it's going to happen on the surface. So if you have a big particle that's thick, the reaction is going to happen on the surface. So if you have porosity, you have more surface area. When you have more surface area, you can have more of the reaction occurring. Likewise, if you have smaller particle sizes and porosity, you even have more surface area. So there's some materials that have like really extreme surface area values. And it's a good way to measure how much reactivity you're going to get out of the material. Again, looking at irregular shaped objects as our real world application. So we want to make sure we can understand how much surface there is there to work with. Because it's going to affect binders, coatings, things like that, and as well as reactivity. So external surface is only dependent on the particle size, but internal surface is the porosity. So how much surface area is inside the material and how accessible is it to the outside? Again, we're talking about specific surface area, which is a unit of meter squared per gram of material. The technologies used to make these measurements are called gas absorption instruments. These are two images. This is the Micromeritics. There we go. This thing's not really, I'm not gonna use it. The TriStar and the Gemini, these are like the basic units used in pharmaceuticals, the most common ones. There's some more advanced ones for other purposes. But basically you have the sample tubes, you have the mass of the material you're putting in, and you're bringing it down to cryogenic temperatures under vacuum, and then slowly dosing nitrogen, like an inert gas. And as it goes into the tube, I'll explain in a few minutes, but as you're dosing it, the quantity, the volume of material gas you're adding to the sample. And when you measure the pressure difference, because a blank tube, you're not gonna have any absorption, but when you have material there, as the gas molecules interact with that surface, they're gonna absorb. And if they're absorbing to the surface of the material, the pressure is gonna be lower than what you'd expect. So as you get lower pressures, as you dose gas, that's absorption occurring. So when we're looking at non-porous materials, we have to refer to it as we're talking about term of average particle diameter. We can relate it to particle diameter with 6 divided by the density and the particle diameter. That's we can get surface area. And the same is true for irregular shaped objects. So from spheres as well as cubes, you can get the same type of relationship mathematically. Again, physical absorption, it's a non-selective gas. So we have an inert gas absorbing to the surface and so you have a gas, which is the absorptive, absorbate, which is the absorbed gas, absorbent, which is the sample. And it's using Van der Waals forces, which is a weak reversible reaction. And like I said, it's under vacuum, under cryogenic temperature. So the absorption will occur. It's a thermodynamic interaction. As they stick to the surface, the gas molecules stick to the surface, we're going to look at how much is absorbed by monitoring the pressure. So this one is actually measuring pressure. This is a little bit more of a schematic of how it looks. So under vacuum, so starting here, you can see a few gas molecules that absorbing to the surface. As you add more gas, you dose more gas, you get more molecules absorbing to the surface. Eventually you get to, so that's a monolayer, eventually you get to a multi-layer absorption where gas molecules are stacking on top of each other. and forming like a thicker, even thicker layer of molecules. So from these calculations, so this is pressure increasing. And then you see from the calculations on the right. You can see the as you increase the pressure, you increase the absorption, you get the multi-layers. And from that, you can get like porosity information and pore filling. So you do adsorption and then you do desorption. And the way we plot those is what's called on the an isotherm plot. And on the isotherm plot, we're looking at relative temperature, or relative pressure here along the x-axis, and then quantity absorbed. So it's basically the difference between the blank. So you're measuring a blank. Sometimes you can calculate it, sometimes you can measure it in situ, or you can calculate it based on the density and volume of your material. But what you're looking for is down here, as you start in your vacuum, you got micropore filling, so it looks like this, where it's filling the micropores. And then you get to a point where it starts building a monolayer, which is kind of coating the surface like in a single layer, and what's called the multi-layer absorption. And then you keep going, and you get pore filling. It keeps going all the way across. And then so you absorb as much as you can, you apply all the gas, and then you do what's desorption. You're slowly taking out quantities of gas. So that's what this other line appears. So this is the pore is now emptying out. So you have a difference here. So you can determine something about the porosity and the pore condensation. So that's the porosity of the material. What we're interested in for surface area is just this monolayer area. So this is the part of the isotherm we can actually calculate. The thing that's interesting about this is that we're collecting isotherms. So we're collecting all of this data, and depending on what we need to know, we could do the full, adsorption, desorption. We can do partial adsorption. We can do the full range of absorption, or we can do everything. And we're taking this isotherm, and there's so many different calculations you can make from it. The BET one is just one specific measurement that you take, which is in this multi-layer absorption area, where it's flat and has a slope. So the slope will tell you something, and I'll show you the calculations. But in general, it's not just one value that you get from it. So you get many values. You can calculate many different things about the surface. BET stands for Brunauer, Emmett, and Teller. They developed this. It's originally developed by Langmuir in 1918. BET model was tailored, advanced a little bit more in 1938. And it's basically, like I said, we're looking at that linear portion of the absorption plot or the isothermal, and we're making some calculations from that. I'm not going to go through all the specific calculations, but it is based on the ideal gas law. PV equals nRT. You can see there's an additional Z value here, which is the compressibility factor from the gas. Because gases typically do not behave in an ideal manner, so we have to account for the different gases, depending on which gas we're using. And what we're looking for in calculating is the quantity absorbed based on the pressure and temperature. So we're maintaining cryogenic temperature, and we're monitoring pressure as we dose the gas. That's really the only measurement the instrument's actually making. And from that, we can interpret all this data. Let's do this real quick. So the final calculation I wanted to show you, surface area by BET. It's basically the monolayer capacity, which is the number of how much molecules you can put on the surface, the number of molecules of Avogadro's number, and then the cross-sectional area of one gas molecule. So in general, if you think about it with this absorption, say if you want to know the surface area of this table right here, and you're trying to measure it based on the number of tennis balls you can stack on it. So you can take each tennis ball, you know how much cross-sectional area there is on a tennis ball, how much space it will occupy on the surface. So you'll just line up the table with the tennis balls, then you multiply that number of tennis balls times the surface area of one, the cross-sectional area of one. That'll give you the general surface area of the table itself. So that's basically what it's calculating based on gas molecules. This is an example report from the software. where it'll record the information. Again, if you want more detailed information on all these other items, we can talk offline. We have plenty of material for this one, to kind of go over it, what all they all need. But in general, I just want to give an overview of this. One important step is sample preparation. Just like any analytical technique, sample preparation is key. We want to make sure that the surface is clean and free from atmospheric moisture or any other contaminants or anything like that. So we have different prep stations. You can pull the sample under vacuum, heat it up, or flow gas over it in order to make sure you prepare your sample correctly to remove any atmospheric moisture or contaminants from the surface, so that the absorption is only occurring on the surface of the material. A practical example of this is when we're looking at something like magnesium stearate for pharmaceutical manufacturing. If you look at this plot here, we're looking at, okay, prepping the sample at 35 degrees all the way up to 125 degrees. And what we found is that, as you keep increasing the temperature of the preparation, the surface area is going down. So what's actually happening is if you look at the particle itself, the material itself, it has some porosity. And as you keep increasing the temperature, if it's sensitive temperature, if it's sensitive to temperature, you could be melting the material and closing those pores up, which is what's reducing the surface area. So how you prepare the sample can also influence, your final results. So you want to make sure that you're preparing the samples appropriately. We have libraries and references on, how you can do that. Typically, most companies will have developed methods on how to effectively prepare their samples for gas detection. Real quick, I'm going to go over some additional technologies. I'm going to jump to density. So when we're looking at density, we can also determine porosity by looking at skeletal density and envelope density. And what I mean by that, those two terms, we're talking about skeletal density or true density. That's going to include, true density is you can consider like kind of like the chemical density of the material. Skeletal density, if you have a material that has cavities on the inside, that's not accessible by gas, for a gas displacement measurement or gas pygnometer, then that volume of those pores are going to be included in the overall bulk material. So you're not going to get what's called true density, you're going to get skeletal density. And then below that, you can see that we have some other measurements. So you have bulk density, tap density. So bulk density is just filling like a container with powder and seeing the volume just basically without, and the volume includes the interstitial spaces between the particles. When you apply a force, which is like tapping or any other kind of consolidation force, that's called TAT or tap density. And then this other one is like if you have, for envelope density, if you have a sizable material like a tablet or something, and it has some porosity, but you don't want to fill the pores. The technique used by this instrument here called the geopig. It has a ceramic material coated with graphite that surrounds the particle and it won't go into the material. So you'll get what's called envelope density.
Is there a specific relationship between skeletal density versus porosity of the material?
Yes. So that's what I was talking about with the envelope density. So what you'll do is like if you have envelope density and porosity. So when we're talking about true density, like I said, it's the chemical density of the material. If it is skeletal density, you have some cavities, but you also have some pores. The gas can go in, but then when you're doing the dry pygnometer measurement with the geopig for envelope density, the pores are not going to get filled, they're going to get included in the volume. So the difference between envelope density and the skeletal density will give you the porosity. So that's it, we get the percent porosity. But as far as making the measurement for skeletal density, it'll have an impact, but the main impact is going to be if it's internal porosity like cavities that are not accessible by the gas. So again, in this image, like I was just talking about with porosity, you do have an influence here. So if you have cavities, these cavities are going to be included as the part of the main material. The gas cannot access these areas, but the gas molecules can access all these pores that are open to the surface. Move along a little bit. This is based again also on the ideal gas law. And when we're taking that into account, we're looking at Boyle's law. P1, V1 equals P2, V2. And as I mentioned yesterday, we have like, these are the schematics. With the schematics, the way it works, like I said, you have the sample chamber, you open the valve, it pressurizes the sample chamber. And it measures pressure, it stabilizes, then you open up the valve in between the reference chamber and the sample chamber. The pressure equilibrates, so you can have a lower pressure. So you have P1 and P2. You know V1 because of the calibration, so it knows the volume of this chamber. But when you have an unknown material in there, you'll get a difference in the pressures, and that'll correlate to V2. So we have P1, V1, pressure 1 and pressure 2. Volume 1 is the calibration, volume 2 will be the unknown. And we can calculate it from this calculation. You can also do the reverse direction as well, where you fill the reference chamber first and expand to the sample chamber. There's some cases where, that's more appropriate depending on the material. But in general, that's how the gas spectrometers work. You want to make sure you have enough sample present in the chamber. You don't want to be close to zero or have an empty chamber. So we do have these types of inserts that can, occupy some of that empty space. So you're not just pressurizing an empty chamber with a small amount of sample, because you want to make sure that there's enough of a pressure difference to be able to calculate a repeatable volume. Also, one of the critical things when you're measuring volume using gas spectrometry or determining volume from gas spectrometry is temperature. You have to control the temperature, or at least take temperature into account, because if temperature changes slightly, the pressure will change for the same quantity of gas. And as that pressure changes, the only thing we're measuring in the instrument itself is pressure. So if we're measuring pressure and not controlling temperature, and the temperature is changing, you're reducing the resolution of the measurement, because the pressure is going to have some fluctuation. And so controlling temperature is critical. The newer instruments now are all Peltier controlled. You can legacy instruments measure temperature, but they're not controlled. But now instruments as technology improved, we can control the temperature effectively. That's just an image of the instrument. I open and close it as a sample. There's very little sample preparation. If you do have samples that have some moisture or something on them, you might want to dry them before you put them in the instrument, because if it dries inside the instrument, you can have changes in volume, like a trending where the volume is decreasing because water or whatever from the surface is coming off.
Analysis there. So can you use the mixed gas as well in this instrument, or has to be pure?
So typically, historically, it's pure gas.
If we pure, I mean, up to 90%.
Usually we recommend about 99%, 99.9%. You can use helium or nitrogen are the more common ones. Nitrogen is cheaper, obviously, so people tend to like that. The system can also use compressed air. It can use, I think, CO2, argon. It just depends. But it's like the typical ones that historically it's been helium. But nitrogen is also, you want to have a gas also, by the way, that's not reactive with the material. So CO2 is there, but not a lot of people use it because in some materials it can actually absorb or react with it. Argon is, sometimes in some applications it's used. And then if you have something with like a membrane where it's porous, you don't want the gas molecules to actually penetrate the pores. So we have the option for using SF6, sulfur hexafluoride, which is a big bulky molecule. And when you use it, it's gonna, you go displace the gas, but the gas molecules are too big to go into the pores. So you can get more of an envelope volume of the material. There's some applications where that's useful. As far as blending gases, you can, but it's not really common. Like I said, air is a combination of nitrogen and oxygen, but the main thing is you have to know, like, properties and compressibility and things like that for the measurement.
So this system comes with the all the calibration.
Yes,
Oh,
yeah, all that stuff's built in. Yeah. Jumping to the geopic, I mentioned this is for envelope density. And you can get porosity when you know the skeletal, density from the AccuPick. It also gives you tap density, which is, if you have a powder, you compress it. The main purpose of this, instrument is we have like this, material called dry flow. And we're looking at envelope density. So if you're looking for like pellets or tablets or something like that, and you want to get the envelope density. I know that, in pharmaceuticals, they use it for testing the ribbons that are used to make tablets. And they calculate the percent porosity. And, the porosity value of the ribbons and the porosity value of the tablets themselves will affect dissolution. And the dissolution, or not dissolution, but disintegration. Because water has to be able to put inside to break it apart. And, if you don't have good disintegration, you're not gonna have a good dissolution. Again, the dry flow is like a ceramic, beads, coated with a fine graphite. So it flows kind of like water, and you're just looking for displacement of the material. Yeah, it's basically it. I mean, that's very simple schematic. You have, you run a blank with the dry flow, ceramic beads. You have the material introduced, and then that difference in volume is going to be the volume of the sample. And from that volume of the sample, because like I said, the particle size is too big to penetrate the pores, so you're gonna get an envelope volume. The TAP density calculation, this is if you're putting a powder in there. So what it'll do is, you'll tell the instrument what force you want to apply. It'll keep applying different forces and look at volume changes and record those volume changes. So the blank will be just no sample at all, so it knows where zero is. Then it'll just keep applying forces when you have the sample introduced. And, you can see it, but what consolidation force, can be applied and what volume you actually get from it. It's common in the pharmaceutical industry. I think the biggest industry now that's adopted this technology is the battery industry, where they're looking at, how much, active powders can they compact in a small volume. And these are just some, applications where we looked at lactose, applying different forces and getting, calculating, the bulk density, compared to the force. So how does it compact well? And this also gives people with information on how it's going to behave when they're looking into the tablet process, where that's what you're going to push the powders together to form the tablet. Looking at calculating percent porosity using the AccuPick and the GeoPick, for tablets and things. So you can look at, you have here the skeletal, density, you have, envelope density, and then from that you can calculate the, percent porosity. Additional tools, if you're looking at, pharmaceutical manufacturing, to kind of wrap things up, mercury intrusion also gives you a percent porosity as well as pore size distribution. This technique is just taking your material and you're applying mercury to it and pushing the pores. The capacitance of mercury, the volume of you're introducing, so you can basically map out the pores in your material. Dry powder rheology, powder flow. How do you understand, how you can measure surface area, you can measure particle size, but when you have a mixture of things together, or how does the powder flow when you're moving large amounts of material, understanding something about the rheological properties of the powder, is important to understand, process control. And particle size, we'll talk about it a little bit. Shape analysis, looking at, particle shape, how does that affect the overall effects of the material? And additional services. So Micromeritics is based in Norcross, Georgia, which is just outside of Atlanta. And we actually have, analytical services. So if you're interested in any of these techniques, but don't have the money or the funding for an actual piece of equipment in your lab, we do offer contract services through our website, and you can, submit samples for a small fee, and we can make the measurements for you on all of these technologies. And just kind of concluding statements, Surface area is a good measure of available surface for reactions. You can, monitor it, how you could compare pharmaceutical excipients. Active pick and geopick gives you skeletal and true density as well as envelope and bulk density, respectively. Combining the two, you can get the percent porosity. That's my information, and thank you very much.
Any additional questions?
As far as I know, roughness, I mean, the surface roughness is contributing to affecting the porosity and the density of material. So do you take the surface roughness and the parameters to calculate the porosity and the other stuff like the other parameters of the sample?
So the surface roughness will affect the surface area measured if you're doing gas absorption. So it'll influence that. As far as the porosity, it's not going to affect the porosity too much, but what the surface roughness will do is it'll affect the powder flow and how the particles are going to interact with each other. So that's why I was like mentioning that on one of those last slides, and all the other techniques. Sometimes you have to make more than one measurement. The porosity value, by itself will give you a percentage, and you have that, number. But knowing something about like surface roughness, knowing how that's going to affect the powder flow or how it's going to affect particle size, understanding surface area. So if you make this all these measurements on the material, you can actually use it to predict what's going to happen in your process. For pharmaceutical manufacturing or whatever it is. And that's why I think I didn't mention it, but the QBD, the quality by design, that's what they look at all these different measurements collectively. And how do we understand, okay, which one's gonna be good, which one's gonna be bad? And it's typical that I've seen, where users will contact us saying like, I'm having this problem. The particle size is passing specifications, the surface area is passing specifications, but I have still random batches of material that do one thing and it's not behaving correctly. And we're not really sure what's doing it, but what can we measure? They can figure it out, so like, okay, well, what are we measuring now? And then let's see what else we can measure. And sometimes we'll just say, send me some samples of your material, and let's look at these other measurements and see if we see differences. And if we see differences in what's good behaving well and what's not behaving well, then we can pinpoint, okay, which critical quality attribute is causing this. And maybe something that you need to start measuring, to prevent these things from happening.
So in general, I mean, because you showed the powder flow rheometer as well. So I mean, how's the adoption in the pharmaceutical industry of powder flow characteristics? And do they kind of compare, for example, compaction that you showed versus the compaction you can get on the powder rheometer?
Yeah, so the compaction on the geopic is at a much higher forces than with the FT4, which is the instrument that I showed in the the FT4 does like 7 or 8 different tests. Some of them are bulk properties, some of them are like air permeability, compaction, all these different things. And the way that works is like it's not just like one measurement. It's you take measurements of different materials and you can look at the behaviors and say, okay, well, which attribute, the feature that I'm measuring, whether this is like compaction or the permeability or flowability and things like that. And pharmaceuticals, when they're moving with large amounts of material, they're using it to design hoppers, they're using it to design, the pipes and how they're flowing these powders, as well as other industries, any industry that's using powders in the process. How does it move? How does it segregate? How does it consolidate? How does it, get affected?
So it gives like the flow energy, I remember, yeah. So is that kind of related to any parameters you're measuring in your other instruments? Or have people tried to correlate things of the powder characteristics?
Yeah, it's gonna vary from material to material, and what you can add to it and blend into it and things like that. So, I wouldn't say that there's art to it, but there's like, it's just so unique, so you have to take all these things into account. Because a lot of times what they'll look for is, when they use like powder rheology and make some measurements, so like, okay, well, which other characteristic is affecting this? Where this one flows well, this one doesn't flow well, this one affects the air permeability of this material, this one is not affected. So is it the surface area? Is it the porosity? Is it, particle shape? Is it, something else? And that's why we have all these different characterization tools to try to, map it out, okay, what is it that's affecting this? And, put it all together, and then with the powder rheology, we're looking at not just the particles, we're looking at the powder itself, like the collection of particles, how they behave with each other. And then if you're introducing, additional materials, additional powders, that could change everything in how it
Yeah.
behaves.
Any other questions? No, thank you so much.
Thank you.
So that's going to segue from talking about powder rheology to actual rheology of materials, nanomaterials and beyond. So our next speaker is Phil Roth from NETS, who's going to talk to us about using rheology to characterize sprayable materials to eliminate sedimentation, optimize atomization, and improve absorption. Phil?
No.
No, because,
Set up the projector.
but we think we need to, yeah, could you share it? Yeah, you share your screen.
You could turn yours off, right? Oh, the host isn't allowing sharing.
You try it.
Yes. Okay, great. Is this a live mic or not?
Oh, if you want to.
No, so I guess I'd use this one. I think.
Yeah.
Yeah. Okay, thank you for coming. This is the last talk, I guess, before the break. Or I guess we moved the break. Yeah. So I'm going to talk about rheology of sprays and how you can use rheology to characterize sprayable materials. Hold on, let me just minimize this because it's showing my screen. Okay, so I'm gonna cover the key rheological parameters in spraying, how to eliminate sedimentation, characterizing the travel distance and atomization of sprays, and then the relationship of viscosity and droplet size of sprays, and formulating to resist droplet runoff. So going to talk a little bit about rheology, but more actually about the applicability of formulating good sprays. So crop sprays and other sprays obviously need several aspects to work well. And one of those is that when you formulated that solution or that slurry, it shouldn't sediment, right? If it's all sedimented, then it's not going to be good because you're spraying just the liquid and not actually the material that you're hoping to spray. Another problem is if your sample is too elastic, sometimes it undergoes syneresis. This is where the phases separate due to too much elasticity. So you see it sometimes with paint. If you take the lid off an old can of paint, you'll see a layer of water on top and then like a jelly layer a little bit below that. And so actually the gel has squeezed together and exudes the continuous phase to the top. And so that's also a problem. So if it's too elastic, you get syneresis. If it doesn't have any elasticity, you get sedimentation. Now, also the spray needs to thin well in the nozzle to be able to atomize well. And then when it's sprayed, it needs to be able to adhere to the surface of the leaf or whatever you're going to stick it onto. And then ideally, it will rebuild slightly so that it doesn't just run off. So there's a few things that we need to look at with rheology of sprays. And we can do all these with rheometer systems. So you can see on the right here a graph of a viscometer range in blue, really just covers a few orders of magnitude from maybe mixing up to high-speed mixing or pouring kind of range. But if you look with a rotational rheometer, you can see really, really low shear rates, as slow as sedimentation, even if something's moving slowly, or sagging, leveling effects, mixing, pumping, and even slow spraying.
Now, if you really want to get really into the spraying high shear rate range, then you need the capillary rheometer. And so that's in black there at the bottom right. So you could say, well, how do we actually correlate what's going on in the spray nozzle to what's going on the rheometer? And it's a matter of shear rate calculation. And so if you're going through an orifice, use the Poiseuille's law to calculate the true shear rate. This is the same formula that we use in capillary rheology. So the shear rate is 4Q over pi r cubed, where Q is the volumetric flow rate in meters cubed per second. You can also get the volumetric flow rate from just obviously the volume. You can measure the pressure if you want and the viscosity of that. If you want to see the shear stress in a nozzle, then you can calculate that from delta PR over twice the length of the nozzle. And so we can calculate easily and simulate easily directly what's going on with a nozzle in a capillary rheometer. It's basically a mini extruder where we're putting a sample in and squeezing it through a die. So it is like a mini spray nozzle. But on a rotational rheometer, we have the constitutive equations similarly to calculate shear rate. And so we can put a sample straight on the cone and plate or parallel plate system and shear it around. And I put up the formulas here for a parallel plate, but the cone and plate aren't much different. And so we can get the stress, the shear rate, and the shear strain from a cone and plate or a parallel plate system. So the first problem that we discussed is sedimentation. Now, with any suspension, you have a balance between the Brownian motion forces between the particles bouncing around and gravity trying to pull them down. And this is on the right here, an excerpt from Terence Allen's great book, Particle Size Measurement, where he actually does a calculation of how many microns per second the particles would move if they're different diameters. And you can see here, if it's a 0.1 micron particle, it's moving 2.36 microns per second just by Brownian motion, and 5 nanometers per second by gravitational settling. So really, obviously, Brownian motion is going to win. There's not going to be much effect of gravitational settling. If you get to half a micron, then you can see that we've got 1 micron per second of Brownian motion and 0.13 microns a second of gravitational settling. So we've got a lot more Brownian motion than gravitational settling, but there is some gravitational settling. As you go to a micron, you can see they almost become equal, 0.74 to 0.55. And then if you go to 2.5 microns, gravitational settling is winning hands down 30 times as much as Brownian motion. So we've kind of got this cutoff range of around 1 micron. So particles above a micron are almost certainly going to sediment unless there's some way of suspending them, right? Smaller particles will sediment very, very slowly, but at 0.25 or less, you probably really don't get much sedimentation at all. They're just going to be suspended for a long time by Brownian motion. So if you do have nanometer particles or hundreds of nanometer particles, and you see sedimentation, it's probably because they're agglomerating. You just need to keep them apart, right? So if you can't keep them apart, then you need to put some body into the sample to keep it suspended. And the idea is that if you have enough structure, the particles don't settle. For instance, if I put peas in water, they settle to the bottom. If I put peas in hair gel, they stay up forever, right? They will never sediment. So if we have some yield stress or gel structure, then it won't sediment. And you actually only need a vanishing yield stress to keep these particles suspended. So here's my formula here. This is my P, and it's got some gravitational force on it, G, and it's got a normal force on it, N. This is from the buoyancy. And obviously we need to then calculate the overall sedimentation stress. And that's the density of the P, rho D, minus the density of the continuous phase times the radius times gravitational constant, 9.81 meters per second, divided by 3. And this will give you, in a dilute hard sphere kind of model, how much sedimentation stress is on that P. And let's say that P is pushing down with 1 Pascal of force. If you have a yield stress of 2 pascals in the continuous phase, then the P will never settle. It will just stay suspended by the gel, right? So we can actually calculate the sedimentation force on any particles. And usually in a suspension, you take the largest ones, right? Because they're most likely to sediment. So you look at your D90 and you say, what's the D90 for this suspension? Oh, it's 10 microns. Okay. So what gravitational force will we have? What's the density of them and the phase, continuous phase density? So I calculate my density difference, the sedimentation stress, and then I know what yield stress I need to keep them suspended. Now you can get the yield stress from a few different ways. And as I mentioned, if the particle size is less than a micron, you just need to stop things agglomerating. You can do that by charging them up. So as a rule of thumb, if the zeta potential is more than 30 millivolts, then things generally don't agglomerate, they stay apart. As soon as they get close together, they start repelling each other. And so it can depend a little bit on the chemistry of what's in, but plus or minus 30 millivolts usually works. Maybe more in some situations or less in others. If the particle size is more than a micron, then you need a yield stress to keep the particles suspended. And sometimes we can put a polymer in there, and the polymer will just tie this whole thing up, kind of create a continuous gel network. We call that polymer bridging, which is actually connecting the particles up. And you can see the picture there on the right, describing how the chains are formed and giving a yield stress. Now, sometimes you can actually affect this just by allowing the particles, the pH to go towards 0. There's what's it called? The isoelectric point. When the zeta potential goes to the isoelectric point, then there's no charge. And if it's a very concentrated situation, then you can use this polymer bridging, if there's some polymer in there, to actually prevent sedimentation as well. So this is a paint, actually, which is quite concentrated. And we found that if we go towards lower and lower pHs, the yield stress actually goes up by polymer bridging. And so in this case, it was stabilized with a yield stress of 15.8 pascals. So the particles clearly couldn't sediment. So there's different ways of thickening up materials. Obviously, you can add guar, gum, and things like that to thicken up suspensions. Or sometimes you can just do it by changing the pH and bringing it near to the isoelectric point. If they're more than a micron in size, if they're less than a micron in size, you need to stay away from the isoelectric point to stop them agglomerating. Okay, so obviously for spraying itself, the viscosity needs to be measured sometimes in the spray shear rate, which is 10 to the 5 to 10 to the 6 reciprocal seconds occurring in a spray nozzle. And most sprays are actually non-Newtonian. So things like water obviously are Newtonian, but most sprays have some kind of thickener in them, and it shear thins as you spray it. And another thing of interest is the extensional rheology. So if you have a high extensional viscosity, then that actually will change the particle size. The more extensional viscosity, you get larger droplet size. And sometimes you can get stringiness even, or a cobweb coming out through the nozzle. So this is if it's really high extensional viscosity, it doesn't atomize cleanly. And you can obviously look at the viscoelasticity and the relaxation time. Now, these are kind of related, right? The more elasticity in there, you'd have usually more extensional viscosity as well. And you'd have a longer relaxation time. And this is all related to the molecular weight of the polymers that you put in there. And they will also increase the droplet size. Yeah.
About the continuous phase. So in the same formulation, how we pick that specific continuous phase, and how we're going to calculate the density of that continuous phase in the same formulation.
So the continuous phase would be water usually, right? Unless you're putting it in a solvent. And then you might add some polymers in there or some pH adjustment buffers and things like that. But it's going to be essentially similar to water because you're only putting in maybe a percent or so of polymer. So I'd imagine that the continuous phase density is usually around 1,000 kilograms per cubic meter. Yeah.
And the temperature doesn't have impact on that as well.
Yeah, it will a little bit, but you can see that. That's something we can look up. Yeah. So atomization quality is obviously affected by the extension of viscosity and also by the shear viscosity. And as you may hear from our particle size colleagues, this is kind of important. And you probably realize that if the particles are very, very small, then they actually will go straight into somebody's nose and then down their trachea and then into their lungs, and they're respirable. So if they're right below 5 microns, they become kind of respirable. And it's a big problem, right, for health. If you're spraying crop sprays and instead of it falling on the crops, it starts to blow off into another field, and then the town next door are breathing all this crop spray, it could be quite harmful to people. So if the particle size is between 5 and 10 microns, it usually sticks somewhere in the trachea. If it's between 10 and 20 microns, they usually stick somewhere in your nose. So if you get larger than 10 microns, then usually things will fall out of the air quickly or fairly quickly. And that's beneficial. It's kind of reducing the aerosol pollution. Okay, so this is some work, photos done by Lynn Walker's group. This was Jenny Christianti, and she shows here on the left a Newtonian liquid atomizing, and you can see it's atomizing quite cleanly, whereas if you make it too viscoelastic, you can see it's coming out as a cobweb. Now, this is an extreme situation, but just to kind of show, sometimes materials don't atomize cleanly if they're far too elastic. And sometimes you get strings forming between the droplets and then they atomize later. And you get satellites and you get a much broader distribution, things like that. So you can generate these high shear rates, though, with the capillary rheometer. So obviously, we also need to look at thixotropy. That's the rebuild time when the material lands on a leaf or something to stop it running off the leaf, and so that it can to stay put. We could have good surface retention, and maybe even look at the surface tension to stop the sample, or to keep the sample to soak into the liquid or to wet the surfaces out. So we can see the storage conditions and some spraying conditions with rotational. We can look at the high shear with the capillary, even up to 2 million reciprocal seconds easily. And I think if you get a super narrow dye, you can go up to 100 million reciprocal seconds. So this is for what we call a power law shear thinning liquid. So materials obviously can be Newtonian, but if they're shear thinning, it's easy to model with the power law model. And we can see here the stress is a constant times the shear rate to the power of n. And so the n value is the power law factor, and that shows you how shear thinning it is. And if you measure different spray materials, oh, I've got the slides in the wrong place here. So this is shear viscosity curves. Obviously, we can have Newtonian, we can have shear thinning. And if you look at extensional viscosity, you can have Newtonian, which is constant. And then you can sometimes also get strain hardening or shear thickening, tension thickening going on in stretching models. So we can look at both shear and extensional with the capillary rheometer using Cogswell's model for extensional viscosity. So we can generate these high shear rates. So this is using a rotational. I just went up to lower speeds here, but you can see here for 2 paint samples that the blue sample here is quite a bit more shear thinning than the red one. And they don't look that different, but when you get to super high shear rates, the blue one really will atomize, much more easily. It'll have a smaller droplet size. The red one won't atomize quite so easily, and if it does atomize, you'd have larger droplet size. So you can see here how they fit with the power law model on the right. So you can run all this in the instrument, just loading, run a test, and then fit the model automatically. So we can do calculations, as we saw before, to look at the shear rate in the nozzle, but you can also correct that for the non-Newtonian nature of power law shear thinning liquids. So if you substitute the n value into the equation here, instead of 4, you can correct the true shear rate. And so I have a model calculation here of calculating the shear rate through a nozzle, and for a nozzle size, and also the nozzle exit velocity. And so you can see that we're in the over 100,000 reciprocal seconds in this range, in this case. There's been lots of different models for looking at the flow through a nozzle, and the extension rate is generally the area of the opening of the nozzle in the inside to the final area. So A0 divided by AF, or AO divided by AF, times 1 over the time, where the time is the time that is going to dwell within that nozzle, you see there. So that's the way you calculate extension rate. And the pressure obviously taken to drive it through the nozzle is the pressure taken up by the liquid, kinetic energy, and the pressure transported out of the nozzle is elastic energy. So that's the equations for that. Doing it on the capillary rheometer, we don't want it to leak past the piston tip, so we're going to use an O-ring or PTFE bushing like this, and you can tighten this up to make it seal in the barrel. And we're measuring pressure just above the die, so it doesn't matter if there's much piston friction. And then we use either an ultra narrow die, which is great if you want temperature control in the instrument. But if you don't really care about temperature control, you just want to do it ambient, then you can actually use a long, thin tube. Now, the benefit of using a long, thin tube is that these HPLC tubes are quite easily available online. And with a 1-foot tube, you can actually generate quite a lot of back pressure and measure it with good resistance on the transducer. If you do block it up, you can just throw the tube away and buy another one for $20. So it's really, really easy to use. And you don't need to do any corrections for the entrance effect. We call that Bagley correction, because it's such a long tube. And the entrance effects are kind of negligible compared with the shear stress of going through the entire tube. So here's some data done with paints, showing shear rates of almost up to 10 to the 6 reciprocal seconds here. And I don't know what that was. Okay. This is 4 millipascal second oil, and this is just going through a 0.2 millimeter die. We see we got to 1.5 million in this test, reciprocal seconds. So that's really directly simulating the spray in the capillary rheometer. In this case, obviously, it's Newtonian, because that's an oil. This is another standard oil after Bagley corrected viscosity measurement, up to 240,000 from 100,000 reciprocal seconds. So this is nice that we can do these corrections and we can do the calculations. This is water using 2 different dyes. So what I did is a long dye and then a slightly shorter dye. And if you deduct the shorter away from the longer, then you can correct. And you can see here I got viscosity of water up to incredibly high shear rates without any turbulence as well. So it is possible to get good data in a capillary at incredibly high shear rates. So this is quite useful because with the calculations, you can see obviously the length of the cone of a spray, the diameter of the cone, and the time of flight of that spray. So obviously we need to know a few things like the diameter of a nozzle, the pressure, and the viscosity of the material, and then we can calculate things. So here's some work done by Pusted. And he shows that for the actual paper's got a lot more detail in it here. But basically, if you know the size of the particles, you can see how fast they're going. If you know the initial velocity of it, you can see how far they're going to fly. So this is a vertical distance of a vertical nozzle sprayed upwards, and the bigger particles obviously went to a greater height than the very small particles. They didn't have as much inertia, but we can see here how high those particles are going to spray up, and the calculations are all in his paper here. So you can do that calculation if you've wanted to see. There's been other approaches as well. This is Gaskins and Filippov, and he looked at time of flight or distance of flight, and you can see if you want to calculate for a certain drop, looking at 25 meters away from the nozzle, looking at a drop of 1 meter, what exit velocity would you need for the nozzle? And there's a calculation for that. So in this case, it would be 55.36 meters per second. So we can calculate exactly how far and how much that plume will spread or drop as it leaves a nozzle. So the influence of elasticity and viscosity on droplet formation has been studied by these guys, Shaw, Park, and Harrison. So for low viscosity elastic liquids, the elasticity actually narrows the drop size distribution compared to a Newtonian liquid. So Newtonian fluids can have pretty broad size range of droplets. If you put a little bit of elasticity in there, you'll get a narrower size distribution. And the spray cone will become narrower compared with a Newtonian liquid. Increasing the viscosity does actually increase the drop size. And so those are the key takeaways from this. So if I spray with any known pressure, here's on my x-axis, the pressure of the liquid going into the nozzle, and then I can see here that depending on the viscosity of the material, I'm going to get different diameters of droplets. So for 1 centipoise, obviously smaller than at 10 centipoise, or smaller than at 100 centipoise. And this has been looked at by Lefebvre in a industrial finishes journal. There's quite a few different droplet breakup models, and I will barely touch the surface of this. Been so much research on, but the common ones used are RATES, which is the wave breakup model. Also the Taylor analogy breakup tab model by O'Rourke in 1987. And then there was an enhanced tab model by Tanner in 1997. So you can look at these. Some key numbers that you may want to use if you're going to look at sprayability are the Weber number, and then the Reynolds number, and an Onisorg number. So these things will characterize the amount of turbulence going on, the amount of elasticity, the delay, the relaxation time, and so all these things together will affect how the material will atomize. And the Deborah number is the relaxation time over the time of the experiment. So the relaxation time of your material over the time of the experiment. And this will show you where the material is going to act like a liquid or an elastic solid. And this is a ratio of the Deborah to Onisorg number, ES. I can't see my notes here. Sorry, I forgot what that's called. Okay, so to get something to atomize well, you really want the Deborah over Onisorg number to be 1 or less, so that it's viscously dominated. If you've really got something highly elastically dominated, then it doesn't atomize cleanly. So you need to be in this light blue range on the bottom right, where Onisorg is bigger than the Deborah number. Now we talked also about surface tensiometry. So in this case, we can measure on the connexus with the Dunois ring. So a Dunois ring is about a 20 millimeter diameter platinum iridium ring. It's easy to clean, And so it's a very standard surface. We can wash it with solvents. We can use a flame on it and make it very, very clean. And then you can put it into your liquid and pull it out. And as you pull it out, it's going to lift a meniscus of the liquid. And from the weight of liquid lifted, you can use the Denoy calculations to see the surface tension. So these are the calculations from Denoy. And this is actually a pretty simple method. If you go to Wikipedia, there's a list of surface tensions for common liquids. And so we can actually check that our results look accurate. We could run, for instance, distilled water and check that you're getting the value of 71.97. And then obviously you could mix up your own sample and check that the surface tension is correct. So we're going to pull up our Denoy liquid through Denoy ring through the surface of the liquid. So initially, as it's moving up, you're just measuring the weight of the ring, right? And we've got a constant normal force there in red. And then as it comes up to the surface, you start to lift some meniscus. You see the normal force start going down, and then it goes through a minima, and then the meniscus snaps. And so we have the area on the left-hand side, which is the ring under the liquid. And then we have this lifting meniscus, and then after it's outside the surface. So the software will actually, obviously this is really small normal force measurements. If you look on the right-hand side, it's very sensitive. So what we're going to do is average the normal force for the first 15 seconds or 20 seconds, and that would be our mean value of the weight of the ring. And then we set a second order polynomial to this and see what the minimum is it. And then that will see the weight lifted. And so we can do the calculation from that. So it's easy to do. You can actually do it at different temperatures as well. See the surface tension at different temperatures, as obviously it is temperature dependent. If you look at this previous list here for water, you can see that the surface tension decreases as you go to higher temperatures. So if the surface tension is low enough, obviously it's going to wet the substrate out. That might also affect the sprayability, but it's going to soak into the substrate. Here's some results I had from a litho etch resist, not really a spray material, I apologize, but I made multiple measurements at different temperatures to see if it was very temperature dependent. In this case, it wasn't. The surface tension wasn't really temperature dependent within the area of the test. Obviously, if it's a water base, it's more likely to be. In this case, it wasn't. Now, sometimes you might want to check the surface tension on a different type of surface. There's a standard surface called a Wilhelmy plate, but you can actually also just get any substrate and coat it with what you want to check. So for instance, if you want to check with a leaf, you could actually just dip your leaf in and out of your spray and see how it's going to stick or whether it's going to wet it or not. And so you could use the Wilhelmy plate type method to see how that sample is going to stick on it. So formulating a good crop spray isn't just a matter of preventing it sedimenting in storage or making it spray correctly, but it's also a case of getting it to stay put on the leaves. And if you add a polymeric thickener with a short rebuild time, it will allow the droplets to stay in situ after they reach the target. They should be able to stick there and rebuild. So it's got just a slight amount of gel structure to keep it in place. And this is kind of a vanishing amount of gel. It's not thick at all, but it's just enough to keep it on there. And so we can do this with a 3-step test on a rheometer. So the first step is incredibly low shear. This is basically storage, right? How thick is the material while it's at rest? And you can see here on the left-hand side, the blue graph is showing it's about 1,000 Pascal seconds. So that's a very thick liquid. And then we spray it right through the nozzle, and that's simulated here, I guess not quite at 100,000, but at 10,000 reciprocal seconds. And so we shear it very fast on the rheometer to simulate going through a spray nozzle. And then we jump back to the really, really low shear rate, here 0.01 again, and then you can see the rebuild time. Now, if the rebuild time is quite fast, within a few seconds, then you could imagine that that droplet is going to spray and it's going to land on the substrate and it's going to stay put. But if it takes quite a while to recover, then it could run off. So you can see this is mostly recovering in the first 10 seconds. In fact, even in the first 2 seconds, you can see it's jumped up by 2 orders of magnitude. So this is quite a fast recovery, right? This is what you'd want if you had a spray. You want it to drop in viscosity and then after it lands to rebuild quickly so it doesn't run off the leaf. It's quite a nice test because before, during, and after, you see exactly what's going on with rheology. And the rebuild time is obviously to do with the polymer thickener in there. Okay, so in summary, I don't know how I'm for time. Oh, 11 o'clock, okay. So we can use rotational rheology to measure the yield stress directly and predict the sedimentation stability of a sample during storage. We can use rotational and capillary together to characterize the sprayability, determine their atomization, distance of plume travel, and droplet size. You can look at the rebuild time with a rheometer to show how well it's going to resist flowing off the substrate. You can also look at surface tension to see if it's going to wet out the substrate well. So rheology really can help you with formulating a good spray, and it can make the test reproducibly, helping with formulation and the processing. So thank you. Any questions?
It's also feel that you kind of with the denoising, you can do also kind of the interfacial rheology as well.
Yeah, so we have a couple of interfacial geometries. One is the Denoy ring, which you could use at the interface. We usually use it on the air-water interface, but you can use a bicone, and the bicone has a good surface area and it has quite a large perimeter. So if you put that at the interface, you can look at oil-water interfacial rheology and things like that.
And how does it detect when it's reached the interface exactly?
So what you do normally is you put the bicone in the lower phase, it's usually the aqueous phase, and you measure the rheology. Let's say it's 10 pascals, and then you put it in the upper phase, maybe the oil phase, and check the rheology, and let's say that's 15 pascals. Now, if you put it half in one and half in the other, it should be 12 and a half, right? Should be halfway between. But if you've got anything precipitating at the interface, obviously the rheology changes. So you'd say, okay, our baseline is 12 and a half pascals. Let's see what's precipitating or what's going on there. If there's a surfactant effects or anything else, you can see that.
And how do you take into account any bulk contribution? It's just the Bosselek number sort of calculation.
Yeah.
Any other questions on rheology in general? Maybe yes, well, great. We don't have to talk only about sprays.
I apologize, I'm not so familiar with this. I did the PowerPoint in a rush, and I'm more of a rheology person, but not really a spray person. So this is a new area for me.
Any other questions? So we can open it up for other questions also from the monomer talks and the micromatrix talks. So there, you guys have any other questions on any application or even limitations? I don't think that one of those limitations. So yeah.
We're real about what we can and then what we cannot.
Yes. I mean, in the afternoon, you guys also come